Okay, so I decided to make a video regarding one of the online homework questions. So we have a tank filled with some type of liquid, and we're given a particular density, 50 pounds per cubic feet, and the tank has radius 2 feet, length 10 feet. I want to calculate the work required to pump all the liquid out of the tank 1 foot above the tank, not merely out at the very top. So the first way to do this is to notice we have symmetry. We calculate the center of mass just by symmetry and go from there. From there we'll have our answer, and then we can use our calculus-based method to show that we can do this with calculus. Alright, so the total weight of the liquid is equal to the volume multiplied by the density. And since we're in pounds, the weight itself is equivalent to force. Alright, so density 50 pounds per cubic foot, length 10 feet, radius 2 feet, and so pi radius squared times length times 50, 2,000 pi pounds. Alright, so work is force applied, in pounds in this case, multiplied by distance moved, and we can think of it this way. Center of the object, move that object up 1 foot above the tank. So this distance is 2, this distance is 1, for a total of 3 feet. Moved upward, we just pull that thing upward, and so 2,000 pi pounds multiplied by 3, and our work is 6,000 pi foot-pounds. I know now you're thinking that seems just too easy. Why are we using calculus? We're using calculus so that we can generalize this to cases in which it's not so easy to just see the solution. So let's do the calculus-based method. Alright, so you notice that I have this on the XY coordinate plane. And so the bottom of this thing is at y -2, top y2. And if we have liquid in this tank, we're going to be pulling liquid above the tank. And so when we start, we pull the liquid 1 foot. Suppose we keep going down. We pull the liquid from here all the way up to here. We keep going down. Pull the liquid from here all the way up to here. We'd like to have an equation that's easy to deal with. So let me show you what I'm going to do. So, of course, this equation right here describes the overall shape, a circle, and r squared is, of course, 2 squared, that is. So now I've solved this as a function of y, because we're going to think of this as siphoning water from top of the tank all the way down to the bottom of the tank. So suppose I'm at a point y right here. Well, then x is defined to be some value here. Now we have the other side of the circle. This equation as a function describes this part of the circle. By symmetry, given a y and a corresponding x, we also have a corresponding negative x when we describe this in terms of a circle. We have two functions essentially. One is x equal to root 4 minus y squared. The other would be x is equal to negative root 4 minus y squared. So given any particular y, we have this distance of x corresponding to that y. And the total distance from one side of the circle to the other is twice this distance. So if we're at this particular point, let me just take this over here. This distance, that half of it, is equal to root 4 minus y squared. And the other half is also equal to 4 minus y squared. So the total distance is 2 times 4 minus y squared. And that's for any given point y that we happen to be at when we're siphoning water out of this thing. Okay, so suppose the tank is, about this full. And now let's consider moving some of the water. So suppose we want to go from here down to here. I want to move that much water. Well, let's pretend that that's a solid piece, some solid rectangular prism or block. And let's calculate the work required to move that solid block from here up to 1 foot above the cylinder. Okay, so let's just take a look at this. Think about what this thing is. So remember that we described the length of, or the distance here in terms of this equation. That distance specifically is twice this. So this distance is 2 times root 4 minus y squared. Now this side length is 10 because that's just the length of the cylinder itself. And we can calculate, because we're thinking of this as an approximation, the approximate volume of this thing we will just call this height delta y, and that will just mean change in height as we move from here to a little distance here. So volume will be this times delta y. I'll just re-express it here. Looking at this picture, I've shown y in pink to indicate a specific value y, and delta y, of course, to indicate a specific very small distance. Okay, so force applied will be the density multiplied by the volume. So 50 pounds per cubic foot, and the constant length of 10 feet, and the width, which changes depending on where we are here. This is the width, and if we think of this as moving this small rectangular prism, like we said, this relatively small height, change in y, or delta y, length, width, height, multiplied by density. So we just rearrange some terms, take all the constants, 50 times 2 times 10, and then multiply it by this term and this term. We end up with, in simplified form, 1000 root 4 minus y squared, delta y, foot-pounds is what we're measuring force in. But we want to calculate the work involved in moving this hypothetical, think of it as a solid rectangular prism, 1 foot from where it starts, 1 foot above the tank. So of course, work is force times distance. So we would like to generically describe this distance moved. So how do we do that? We have a generic y value here. And we know we want to be 1 foot above the tank. So in terms of the equation we have to describe each half of the circle, and in terms of this arbitrarily chosen point y, highlighted in pink, how do we get a generalized expression for force times distance? We have this expression for force, but what about distance? Well, remember that this tank has radius of 2 feet. So from the center of the tank to the top on this coordinate plane would be from 0 up to 2. We want to move this generic arbitrarily chosen rectangular thing up to 3. And then let me just label this -2. Alright, so moving from here to here, I've got this arrow thing describing this distance. If I start here and I move up here, how do I describe the distance? Well, I've moved all the way up to 3, and I started at y. So the difference between this point y and this point 3 happens to be the distance. The difference between the 2 points. 3 minus y. The distance is, we'll say it again, the difference between the point to which we're going to move and the point at which we start. This holds true even if we start down in the negative. For example, suppose we started all the way down here. The distance we would move would be 2 plus 3, that would be 5. The difference between 3, the top point, and the bottom point, the difference between that would be 3 minus -2, which would be a total of 5. So here's our generic equation or expression for distance moved in general. Okay, so work is force times distance, and we've given a generic description, 3 minus y, for the distance that our hypothetical rectangular slab would move. And I'll just say it again, force is density times volume. Volume was this distance, so for a given y value, we have this distance times 2. We have the length of 10 that's constant, and we have small height, delta y, and we have density 50 pounds per cubic foot, and that's where we get the 1,000, 50, we have the 2, we have the 10, we multiply all those together, we get this. And so here is the force required to move this thing, and here is the distance we are moving it. Now I'm going to rearrange a couple terms. Alright, and I will do this because we will express this in terms of an integral. So this approximation method would give us a fairly good approximation of the work that we're asked to find if we were to have a relatively large number of these small rectangular approximations. So this would always be described by this. This length would always be described by 10, and the distance moved from any point y would be described by 3 minus the point that we're at, the difference between 3, where we move to, and wherever we are. Delta y, however, this is just a concept. As this approaches 0, i.e. as we estimate work done over and over by moving small rectangular components, as this goes to infinity, we essentially have an infinite summation, and we represent that by the following notation. So the integral from our lower point, -2, to our upper point, 2, so the lowest point would be 2, the highest point would be, -2, highest point would be 2, and instead of delta y, we end up with dy, the integral of all of this stuff with respect to y. And now I think you might remember, you might be wondering, well, you calculated the work earlier. You had something in terms of pi. You had, there's no pi anywhere in here. Well, if you'd like to see the integration, if you'd like to see the result, then just please continue. Otherwise, try to work this thing out, and you'll discover that because of the way this equation is set up, this describes something to do with area of a circle. You'll end up having pi in your answer. Okay, so let's see how to deal with this integral real quick. Move this out of our way here. So notice that our integral can be broken up into two integrals. Okay, so here's our integral all set up, and we've got it divided now into these two components. So right here we've just multiplied by 3. Right here we've multiplied this whole thing by -y. And so this is plus the integral of this stuff multiplied by -y, and we can just re-express it as minus this. So now notice this. I've taken the 3 and the 1000 and multiplied them together. To get 3000, I've taken the constant to the outside. I'm going to focus on this integral right now, without having to do anything other than just recognize the implications of this formula. How do I get this? Well, take a look at this. Recall what we were talking about before to describe the top part of a circle. Right? X squared plus y squared is r squared. Well, in our case, radius is 2 in our case. So, anyway, this describes the top half of a circle. And these limits are from one side of that to the other. Now remember that the integral can represent area. And since this describes the top half of a circle, and we integrate from one side to the other, this represents half the area of a circle. This means this should give us, with our constant on the outside, 3,000 multiplied by half of the area of a circle, pi r squared. Radius is 2, so that's why we have this. And then this, of course, is equal to 3,000 times 2 pi, and that's because 2 squared is 4, 4 over 2 is 2, and so this is 6,000 pi. So this is exactly what we got through our logical reasoning at the very beginning before we did any calculus. But you're probably asking, well, wait a second, what about this? This thing just disappeared? Does it seem that we left something out before? In fact, no, we did not. Let me show you what's going on here. We integrate from -2 to 2. Now, this thing will end up breaking up into two integrals. 0 to 2, 1,000, take that on the outside, root 4 minus y squared y dy, and then this will be plus the integral of -2 to 0 root 4 minus y squared y. Now notice going from 0 to -2, so for any y values here we have the same thing, positive. But for negative y values, we have the y on the outside. This entire expression is negative. This will cancel out with this, and I will show you. We can just re-express this. From 0 to -2 would be the negative of this integral from 0 to +2. So in this, once again, this is the 1,000 factored out. So we've got this minus itself, and we get cancellation. This whole thing becomes 0. This thing is here as an artifact of the algebraic expression. So this does make sense that we have this here, and if you do this integral by u substitution, you can set u equal to that, and this y will cancel out. You'll get something, and you'll end up with 0 as your answer to this, so you can confirm it that way. Anyway, I hope this has helped you understand this, and I will see you in class.